Good afternoon, and thanks for joining us. I want to introduce myself. My name is David Williams. Give you some history and background on myself. I spent 10 years in the United States Navy, where I graduated from the Navy Nuclear Power School and operated nuclear reactors for 10 years. After getting out of the Navy, I took a job writing control and logic. Did that for 3 years before I took a position with OMART and started working on nuclear detections. At that time, one of the first jobs I had at OMART was to work on the delayed coke level measurement system. After working about 17, 18 years with OMART, I left and went with Berto. The main reason I left Berto is that the main focus of Berto Technologies is nuclear detection, and it fits my background because I have my degree in nuclear engineering, where I spent about 35 years of my life doing radiation measurements and radiation detection. So today we're going to talk about who is Berthold, why use radiometric devices at all, briefly describe how they work, and then which are the main applications that we use in specific process units that's geared toward heavy oil opportunity crudes. So we're going to talk a little bit about desalters, delayed coking, SDA units, solvent deasphalting units, and then resid hydrocrackers. When I talk about resid hydrocrackers, there's both ebullated bed and also slurry. So we're going to touch on both of those because they're very similar to each other. So who is Berto Technologies? So Berto Technology is a company that was founded in 1949 in the Black Forest of Germany. We've been providing high quality nuclear measurement devices since then. We're the oldest and largest radiometric measurement device company in the world. We started our history back in 1949 when Professor Rudolf Berthold was approached by BASF at Luxemhaven's chemical plant, and they had an issue, so he would develop a high level switch at that point, and then that was the start of our path into the nuclear gauge industry. We have several buildings. We have over 350 employees. We also have subsidiaries. So we have several subsidiaries around the world, so we are able to help our customers no matter where you might be located. We have offices in Germany, Austria, Belgium, China, France, India, Italy, Norway, United Kingdom, and the United States. And for areas that we have outside of our subsidiaries, we have very large rep organizations that covers our territories like in Mexico, Brazil, South Africa, Australia, and places like that. So we can provide support and services no matter where you're located. I briefly touched on the history where we came from. As I mentioned, Professor Dr. Rudolf Berthold founded the company, and then, as I mentioned, we had BASF had an issue, and we was approached by them to provide a level measurement solution for them. Some of the other unique things that we have in our portfolio that we've used over time is using rod sources where we can take cobalt wire and wrap around, and we can customize the activity along the length of it for specific applications. We do have something we call the SuperSense, which is the most sensitive detector on the market. This allows us to continue using sources for extremely long amount of time or use very low source activities to provide a very repeatable and reliable measurement. And then also we have SEAL2, SEAL3 on all our detectors that's continuous level switches, and also density applications. The main thing that we have is we have over 70 years of experience as a company. We have several individuals within our organization that's been doing nuclear gauging and applications for 20, 30 years. So we have by far the most amount of experience and knowledge when it comes to applying radiometric devices to your process solutions. So who do we provide measurements to in the refinery industry? As you can see, we provide across the globe to various organizations around the world, from ExxonMobil, Petrobras, YPF, Pemex, Lukoil, Petrom, OMV, MOL, Indian Oil, CNOC, SR, Petro-Canada. We have a vast portfolio of stuff that we provided to some of the big name players in the industry. Some of the other industries that we do besides the refineries, we do chemical, petrochemical, steel, mining. We also do offshore coal gasification, power plants, pulp and paper, sugar, and glass production. So a little bit of the nuclear gauge history. In the past, there's been a lot of companies in the North American market that are no longer viable options. And so it's important to understand there's basically only 3 large corporations that do nuclear devices anymore, which is Berto, Vega, and Anderson Hauser. But in the past, you might have heard of names like Xray or Xray or Texas Nuclear or Thermo Fisher. All those companies are no longer providing nuclear gauges to the industry. The last one that went out was Thermo Fisher, where they made the announcement last year that they're no longer providing nuclear gauges. And they was the biggest provider of the Neutron Backscatter devices into the delayed coatings. So this just shows you along the time frame what companies started, which companies ended, which companies bought which, and now we're to the point where there's basically 3 major providers. So why use Radiometric in a refinery anyway? Most of the level measurements are currently done by differential pressure measure, displacers, floats, magnetic level indicators, capacitance, radars, and guide array radars. It used to be the term in the industry that we had that when all else fails, you nuke it. The nuclear gauges, or radiometric devices are very repeatable and very reliable. So that was the mantra that people had, is that if you couldn't get any other level measurement technology to work, go ahead and apply the nuclear technology. So like I said, as all else fails, nuclear, but sometimes they're by far the best devices to use when you have applications with high temperature, when you have applications with high pressure, buildups, when you have product that has buildups where if you have come in direct contact with the fluid, it causes issues with either plugging pressure port or causing floats to stick. So since the nuclear gauges are non-intrusive, they do not have that issue with the buildup. Same thing, they don't have the issue with the pressure ratings because these things are non-intrusive to the vessel. You don't need a process connection. And then if you have a toxic or dangerous chemicals, some of those things are like phosgene, hydrofluoric acid, hydrogen cyanide. Whereas, as I mentioned, since these things are non-intrusive, do not need process connections. Less process connections on a vessel means less possibilities for leaks. So I'm just going to go over and talk about how nuclear gauges actually work now. So a brief description of how the nuclear technology work is that you have radiation being emitted by a source, a radioisotope, and those gamma rays are interacting with the scintillation crystal. Scintillation is just a fancy word, means light giving. So when that radiation interacts with the scintillation crystal, it gives off photons of light. The photons of light are then captured by the photomultiplier tube where they get counted and sorted. So you have more radiation applied to the crystal, you would have a higher pulse rate. How many counts per second that you have increases. When you have less radiation imparted onto the crystal, you're going to have a lower count rate. So when you have a vessel, you mount the sources on the outside of the vessel, and then you mount the detectors on the opposite side, and we transmit radiation from one side of the vessel to the other side, and we detect that. So in the nuclear gauging industry, when we have more radiation to the detectors, that means there is no process in between the sources and the detectors, so you get the full amount of radiation to the detectors, so you have the lowest level. As the process starts filling, you start attenuating the radiation from the source to the detectors, and therefore the detector has a less radiation to them, so the count weight goes down. So when you have different sources, different configurations of sources where we have a narrow beam, we have a fan beam going over 30 degrees, 45 degrees, we have a rod source, and then we have sources where we can mount inside the vessel, which is called the flange shields. And then you have various number of detectors that we have, point detectors, relatively short rod detectors, and very long rod detectors up to 8 meters long, 26.5 feet. We can come up with multiple combinations, variable different geometries that we can make the measurement. And each one of these measurements has a unique property that makes them advantage or disadvantage when you're trying to measure a certain product per se. So one of those is, just to give a good example, is if you use a rod source and a rod detector and you have solids, especially like in a catalyst hopper and a CCR, and you have a coning material in there. If you use the traditional method, we have a point source and a point detector, and a rod detector, I mean, you would have radiation coming down the backside of this slope. You're not really tracking the top level of this cone. But when you're transmitting radiation from a rod source to a rod detector, you have radiation going straight across the vessel, so you're better able to see this top portion of the level measurement. So there's times where you need a different geometry to make a measurement better, and other times you can use one that is standard, which is the standard one that's in the industry is the point source and rod detector. But with us having more tools in our toolbox, we can apply things and use the proper tools for the proper application to give you the reliability and precision that you need for your measurement. So one thing that needs to be taken into account when you have nuclear gauges is, how do you control the sensitivity due to natural changes and also due to long-term drifting of the PMT. One thing that we use that's very unique to Berto is we use cosmic rays compensation. So basically, this is really good for low-level switches, level gauges, and belt scales. So what we do, we have a known reference, basically. So as I mentioned before, as a scintillator works, you have gamma interacting with the crystal. And then we also have the cosmic rays reacting with the crystal that gives us a higher threshold, a higher pulse height. So now this cosmic ray becomes our reference. So now we have a count weight from our source ourselves that we're using to make the measurement. And then we have a count weight from the cosmic radiation, the background radiation coming from deep outer space. And that's been a constant value for millions of years. So we can use this as a set reference. So when you start seeing changes to the PMT due to temperature changes or due to long-term drifting of the PMT, as I mentioned, all PMTs have this long-term drifting issue. So as the count weights are reduced due to either temperature or this long-term drift, we can see that on the reference counts that we have from the cosmic rays. We calculate that, and then we apply a voltage correction to the PMT to account for those count weights. So now we bring our count back to the normal value, and our measurement counts are back to normal measure. This what allows us to have extremely long-term stable gauges over the life of the device. So no constant repeat calibration on devices. You don't have to worry about devices drifting or moving with temperature. It's very repeatable and very reliable for the long term. The other thing that comes across is when people are doing radiography, sometimes people refer to it as X-ray or NTT testing. So they are using a gamma source, and when that gamma source emits the radiation, all detectors detect that radiation, and it has an effect on level measurement to go to a minimum value. Some of the most common sources that they use are cobalt 60 source, iridium 192, and selenium 75. And when they're using these sources for these NTT or radiographic testing, they are using extremely high levels of mounted radiation. The, the largest sources that we use typically on a coke drum application might be a 3 Curie source, but as you can see, when they do NTT testing, they can use anywhere between a 50 to 100 Curie source of cobalt 60 or 100 Curie source for iridium 192. So these are extremely large sources compared to what we use for the application. So the amount of radiation that they put off can be relatively high, depends on how far you're away. So this is the formula that you use to calculate how much radiation that you can get from a source at certain distances. I did the calculations for you. We typically size all sources to have around 0.5 microsieverts per hour, which is 0.05 mR per hour. So if we have a 100 Curie cobalt source being used for NDT testing, and you have a field of 0.5 microsieverts per hour, that means that source is 1,652 meters away from you. So that's 1.6 kilometers. So this radiation does travel extremely long distances, and this is the reason why some devices have issues with NDT testing in the area, not just in your processing unit itself, and it might not even be in your own refinery. It might be the chemical plant or the refinery next door who's doing it, and it's affecting your nuclear devices. So if you have 0.25 microsieverts per hour, so that's enough. If your level gauge is reading 100%, that's enough radiation to drop that level from 100% to 50%, or from 50% to 0. So in a case of a vacuum tile bottom measurement or a fractionation tile bottom measurement, that's going to have a 50% offset in your output. So that means your control valve is going to try to open to fill that back up, where you can now overfill the vessel and flood the tower and flood the trays, because it's actually reading 50% low. And you can see at this 0.25 microsievert per hour, that's a distance of 2.3 kilometers. So for the different energy values that you have with cobalt 60, iridium 192, and selenium, cobalt is by far the most energetic, so it has the highest field at the longest distances. So as I mentioned, for 100 Curie cobalt 60 source, 0.05 mR per hour at 1,652. Iridium 92 at 100 Curies puts off a 0.05 mR field at 1,098 meters. Selenium 75 puts out a 0.05 mR at 242 meters. That's due to the energy values of the individual isotopes. So to give a frame of reference, here's a picture of a refinery. The shaded area is a delayed coker area. So now here's an overview, a larger from a zoomed out version. So the shaded area is the delayed coker area. So if anybody's testing inside this red circle, this has a radius of that 1.6 kilometers. So if anybody's doing any type of NDT testing in this area, it could affect the gauges that are mounted in the unit in the shaded area, because this will still put off that, as I mentioned before, that 0.05 mR per hour on that detector. So that's enough radiation on the detector to take it from 100% to 0%. So we do have advanced algorithms in our devices that will minimize those effects and almost prevent them altogether. So when we use these things, radiation comes across, our detector sees it. What we do, you can see the count rate automatically increases the high thing, and when that count rate increases, you see the 40/20 level drop off in time. So what we do, we have an advanced algorithm called Xray interference protection. So the other thing that we have is that our detectors do not go into saturation and do not get damaged by excessive radiation and then lose sensitivity. They're very stable over the long haul of the device, and is due to the PMT selection and PMT size. What we do is when we're taking this measurement, you see here, this red line is a live active measurement. We calculate a limit, and then as it basically goes outside that limit within a certain amount of time, we look at a rate of change per se. So when a count rate jumps outside that limit within a certain amount of time, we know that extra radiation is coming from NDT testing. So then we can lock and hold the last process value, and then also send a digital signal to the DCS to let you know that the system is locked and held and someone's doing NDT testing. Once the NDT testing is done, the count rate comes back below that threshold value. The device waits a little while for those count rates to be purged from the system, from the calculations, and then resume radiation level detection as normal. And this is a standard feature that we have in all of our detectors, so we can turn it on, and that way you can have some peace of mind that when someone's doing ET testing at a refinery or chemical plant next door, that your level system is not going to fall off to a minimum level and cause an upset condition per se. And as I said, this is an internal algorithm that we have inside of our device, so you do not need an additional detector to do this detection for you. Every single gauge, a standalone gauge, can do it by itself. So what are we doing? Where are we at inside of refineries? So some of the main process units where you refine nuclear level detections are the salters, the crude towers, the vacuum towers, delay coking, solvent asphalting, alkalization, both sulfuric and hydrofluoric, resid hydrocrackers, ebullated bed and slurry, FCC units, and then also CCRs and the reformers. The ones that we're going to talk about today, which are more or less the ones that people have for the configuration if they're processing heavy oils or opportunity crudes, is the desalters, crude towers, delayed cokers, solvent asphalting, and resid hydrocrackers. So the desalter solution. The desalters are the first processing step in the refinery. As the oil comes into the refinery, it gets mixed with a little bit of water to help remove the salts. If you do not have proper control, or if the thing is not designed correctly, you have the potential to have issues with water level getting too high, shorten out the grids, causing carryover of both water and salts and minerals. All these things have a detrimental effect to the refinery. Waters can cause problem in the towers by flashing, causing tray damage. You can have carryover of water and salts that creates acid and cause corrosion issues. You can have those minerals and causing problems with fouling and of heat exchangers and furnace tubes. And then also the catalyst downstream can also be affected by any of those minerals being carried over. One of the things that can cause issues within the desalters themselves, if you start mixing different types of oils, you have compatibility issues between different types of oil. You have oil that has high tans. Like I said before, with heavy minerals, they cause issues with the separation. Chemicals, especially coming down from Canada, they have all kinds of chemicals that they add for stabilization, demulsifying, flow enhancers, and all those chemicals have potential issues with causing emulsion to basically stabilize or more difficult to separate. And then also different types of oil itself has conditions that it, like high asphaltenes, where they causes issues with the emulsion to basically be more difficult to separate over time. As I mentioned, when these things comes in, they stabilize. You have more mud that's being built up. Water does get to the grids, causes voltage spikes and stuff. So having a proper control, proper understanding what's happening in the salter is critical to make sure that it's operating correctly and you do not have these issues with the corrosion, fouling, and catalyst poison. So how we do it, this little video shows uh, how we do a measurement in the desalters, where we have a dip leg inside the vessel where we have the sources, which does not come in contact with the fluid. And then we have the detectors mounted on the outside for ease of maintenance and ease of replacement. So each one of the detectors measures a density value. Then we use some advanced algorithms to use these density values in the spacing between the detectors to calculate water height and emulsion height and provide a 40/20 output so you can do your control for your water level control. And then also chemical companies can use the emulsion height to do calculations about how much chemicals they need to add and what chemicals they can add. So as a brief synopsis, these are some screenshots that we have of our little algorithm computer evaluation unit, where we have the density profile, and then we calculate the height of the water and the height of the emulsion, and then generate a 40/20 for each one of those signals. So the one thing our system does that most of the other technologies out there, like a guide array radar, displacer, AGAR systems, we track both interfaces. What I mean by both interfaces is that there's an interface between the water and the emulsion, and then there's another interface between the emulsion and the oil. All the other technologies out there only provides one output, and that output is going to be someplace between those two boundaries. So if you have a relatively stable emulsion layer where it's only 6 inches, the other technology is going to be someplace in the middle, so it's not too far off. But with all these other conditions that's happening with crude oil compatibility, um, the chemicals coming down through the flow enhancements and stuff, they cause that emulsion can actually grow to 36 inches, 40, 45 inches. And so it's still going to track someplace in the middle. So our system will let you know where the top is and the bottom. So by knowing where these things are at, you can minimize your grid shortages. You can increase stable control to help remove the salts. And also, when you're removing these salts, remove these waters, you can reduce the downstream corrosion and prevents upsites and stuff. So it's valuable to know exactly what's happening inside the salter so you can operate it more precisely. Delay coca levels. And in the DCU, main applications that we have in the DCUs is the coke drums themselves, but also fractionation tower. Sometimes we can look at doing the blowdown cellular. We can do belt scales for the coke handling. There's all kinds of applications we can do in the delay coking unit. As I said before, Thermo Fisher made an announcement early last year, that they're no longer going to provide nuclear gauges in the industry. So for the longest time, Neutron Backscatters was the device for choice to make the measurement in delay coking. So since there's not anybody out there providing the Neutron Backscatters anymore, a lot of companies are looking for replacements. So when we have a continuous level on our level system, typically we see arrangements similar to this, where there's 3 Neutron Backscatters located at the top, one located at the bottom sometimes. When we have our level system on it, we can put point level switches at the same elevation to simulate the neutron backscatter. So when we have our sources mounted on the drum, so we can do the continuous level, we have a constant area of radiation across this whole span, so we can put level switches anywhere along this span to provide outputs for those certain elevations. So by mounting point level switches at these elevations, these point level detectors can mimic the output from the neutron backscatters, and then you still have the continuous level along the side. Like I said, we do the continuous level, and it tracks the top of the foam as it comes across. So the level is tracking the foam. As you add anti-foam, we would track closer towards the coke bed itself. It can help because you can determine the rate of change, because since it's tracking the top of the foam, you can see how fast it's coming up for foam ups. Or when you hit it with anti-foam, you can track, see how far it comes down. You have a continuous reading. It's not just a localized area where I know I got level here, but it's not here yet. How fast is it coming up? You can see that over rate of change. So now that you have a continuous level, not this point, you can use the gamma continuous level system to have better drum utilization. That means you feel more into the drum. So now I have continuous level along the side. I can actually increase and go a little bit higher if I needed to. You can help prevent foam overs. Foam overs are very costly to clean up, a lot of manual intensity to clean up, and it can be down for 2 to 6 weeks, and it is can be really, really expensive for a refinery to have a foam over. By having the gamma continuous on it, you can see what the foam is doing over time, and you can have a better understanding of what's happening and prevent the foam overs. You can also optimize your chemical usage for anti-foam injection by looking at how much foam that you anti-foam you're adding and how much foam layer is dropped, since you do have it along the continuous range. I see that I injected 2 gallons an hour and I saw a 5-foot drop. If I inject 1 gallon an hour and I see a 5-foot drop, it's basically doing the same thing. And as you guys know, that if you can minimize the amount of anti-foam usage, you help increase the life of catalyst downstream. So the main advantages of using the continuous levels on the coke drums is increased coke capacity, increased reliability, and then you also can optimize your anti-foam usage. Another application that we can do is solvent asphalting. This is an extractor that you see a picture of here. So in the solvent asphalting unit, you basically have an extractor, separator, pitch stripper, and maybe a DO stripper. So the extractor is an interface level, and the other ones are more like fractionation towel bottom level measurement or vacuum towel bottom measurement. The one that we see a lot of is the extractor measurement, since it's not necessarily a clean interface. It operates under relatively high temperatures and pressures. So we can insert a source from either the top, bottom, or side, and you can do it several different ways. It depends on your application, if it's a brand new vessel or versus a retrofit of an existing vessel. Um, Sometimes when it's retrofitting of an existing vessel, we have to make do with what nozzles we have available. Like I said, we can put it from the top, bottom, or the side. We can use a single point with 2 detectors. So as my level is changing up through this area, this detector seeing this change in radiation. And as my level passes past this point, this detector sees that change. So you get a continuous level reading throughout the whole span using a single point and 2-point detectors. Or we can go back with multiple points of sources inside the vessel, and then you have a rod detector on the outside that comes across and measures the continuous level inside. So there's various ways to doing it. This is the main way that we do it with new vessels being under construction. With existing vessels, we have to make do with what available nozzles we have is available to us. We use hydrocrackers, both slurry and ebullated bed. So we typically have Debolated Bed inside. It's kind of sort of like a multi-phase level measurement system we use for the salters or alkalization units, where we have multiple density gauges mounted on the outside, sources mounted on the inside, and then we're measuring densities at various elevation points to determine what's happening inside the reactor. Typically what we see people to do is not necessarily operate for level control, but also some advanced controls I'll talk about in a minute. But typically what we see is there's 65 kg per cubic meters vapor. Then we define what foam is, we define what hydrocarbon liquid is, we define what ebullated or suspended catalyst is, and then we also have what we call a slump bed. So when we're out there, you have this one here is measuring vapor density per se. Now this one's measuring foam. The next two are measuring oil. Another one is measuring oil and catalyst. So if you have a slump bed condition, that means you lost your suspension of your flow, and that density is going to get really high. This catalyst is going to pack up, and then the density is going to go higher. So that gives a good indication of a slump bed condition. So level control is important on this because if you get too low, you can get the slumping of the bed per se, poor distribution of catalyst, and this creates hot spots, causes the reaction to go very fast in those areas because you get very close contact with stuff. If you go too high, you can get catalyst carryover into your recycle cup, which can cause to pump damage, and then that requires a long repair time to repair the pump that might be caused damage caused by the catalyst. If you have an extremely good measurement on the devices, understand the dynamics about what the hydrogen effects are to the density gauges, you can increase unit performance by doing vapor and solid hold-up calculations because you have a very precise measurement. So you get a good resolution on your density gauges, and you can provide these advanced calculations to increase the unit performance. Thank you for your attention. If you have any questions, stand by for the Q&A. We can answer questions on the applications we talked about, the process units we talked about, or any other thing that you might have in your refinery. Thank you.